ಅದನ್ನ ಇದರಲ್ಲಿ ನಾನು ಹೇಳೋದು those are the only 3 people who had said. I think there was one other person who's no. I had asked who would show up. Okay, it's, if I should, huh? Huh? இல்லையே சரியா இருக்கே இதுல இதுக்கு மேல நான் ஒன்றும் பண்ண முடியாது. இதுல மியூட் பண்ணிருக்கேன். see last time கொஞ்சம் இதுல ஏதாவது இருக்கோ? இதுலயும் நான் மியூட் பண்ணிருக்கேன். ஓ ஹலோ, எப்போ சரியா இருக்கு இல்ல? Okay, I think Santhan, I think I can't. I don't know if I can repeat simplex. Okay. So, simplex is fine. Okay. Yeah, I'll just summarize Reluplex. ஏது வருது இதுல இல்லையே, அதுல இருக்கா? Okay. Yeah, I think maybe I will, when I go through the example. Yeah, in the book, right? கொஞ்சம் வெளியில இருக்கட்டும்ன்றீங்களா? Yeah, I think the one key point maybe that you missed that I can do is, what was the example that I used? Suppose you have x is equal to y and the simplex LP solvers do conjunction of the, they can solve conjunction of linear inequalities. Okay. So Z3 can do these kinds of things. Okay. This is OR. Yeah, I'm lazy to write the logical AND. Now, you need this for doing DNN verification, right? Because the DNN model itself, although all the internal nodes, I mean, except for the ReLU nodes introduce nonlinearity, which is expressed as if then else, okay? So that can be modeled only as using implication. Therefore, you need LP. I mean, LP solver itself cannot do it. No, Z3 can do it, and I showed the architecture of thing early on in one of the lectures because it has the DPLL for which you were there, I think. No? That is the proposition layer it has, and the DPLL layer, slight extension of which is interacts with theory solvers like LP solvers, etc., is able to handle these kinds of arbitrary propositional structures in which the atomic things are drawn from some theory. In this case, we are interested in linear inequality over arithmetic. Okay. So the question is, how do you this? This is a repetition, okay, for the rest of you. So one way of doing it is, like you said, you could replace this for each of these things. You can just retain the propositional structure. Okay, you can use the simple propositional SAT solver to get a satisfying instance of this. Okay, this is one satisfying instance, B1, B2, and B4 is another satisfying instance. Now, this is a propositional abstraction. They call it an abstraction because it throws away some detail about the fact that these actually represent linear inequalities. So, this one, in order for this to be true, this propositional structure has to be true. But then additionally, you will have to check if this one preserves the, is true in the theory of linear inequality. Okay. So now if you check this, this is X less than or equal to Y and Y less than or equal to Z. And this one is, let me take it as B4. Okay. So that is X greater than Z. So that cannot be true. That's because, in the theory of linear inequalities, because of transitivity, X less than or equal to Y is, and Y less than or equal to Z implies X less than or equal to Z, and therefore there is a contradiction. Okay. So, in the naive case, you could combine this DPLL with the theory solver by actually querying for each of this, for each of the thing. And that is like, it's as though you are case splitting. Okay, so this is checking for each of these things and expanding out is like you take, I guess Arpan, I don't know, someone answered last time. So you could take for each of these disjunctions that you have in your formula, okay, or the equivalent of disjunctions, you can split on these two things. You can first take the case where X is greater than Y, then take the case X is greater than Z and the rest of the conjunctive fragment. And then you can, check if each of those case split, each of those instances of LP that you get by splitting, considering the case that you could do. So that is a naive way of doing it, because then you can see that depending upon how many disjuncts you have, disjunctive structure that you have in your formula, your, the number of case splits will be exponential in the number of, these conditions that are there in the disjunctive clause, which is what you want to avoid. Okay. So that is, said it. Now, Z3 avoids it by using certain, propagating certain theories. Okay. Instead of enumerating, instead of doing all the case splits, it kind of, the basic idea even there is to delay the case splits. Okay. So try, once you know that you have got a partial assignment B1 and B2, you try to propagate the the consequence of making this assumption, B1 and B2, in this case, X is less than or equal to Y and Y is less than or equal to Z. So, and try to derive the implications of those things, which in that case, you could, from the theory, like you can make an extension of a LP solver. Okay, LP solver can actually be made to give you consequences of these, the partial assignments that you make during the DPLL, which in this case, you can now derive that, okay, this implies X is less than or equal to Z, and then actually add it, which boils down to learning that not B of 4 is true. And the moment you add not B of 4, you eliminate it. That is one way of eliminating K-split. That's what, which I have not discussed, but that is the idea that Z3 uses. Now, what Lec16 tries to do is, you can, of course, do this kind of K-splitting and decompose the checking of satisfiability of this one into checking an exponential number of LP instances, potentially exponential number of LP instances, exponential in the number of these atomic formulas that appear in your disjunctive clauses. Okay, and Lec16 tries to avoid that by using this concept of lazy K-splitting. Eventually, in the worst case, as Arpan, you observed, you will end up having to consider several cases, but try to see if you could construct an over approximation, much like what was done here. Okay, this I consider as an over approximation of this. Okay, in the sense, any satisfying instance of this will also satisfy this, but any satisfying instance of this may not satisfy this. If this is unsat, certainly this is unsat as well. Okay, and that's what is the property of over approximation is. And try and construct an over approximation of your DNN model. Okay, which is an LP instance. Okay, which is just a conjunction of inequalities. Solve it using LP, and the way it constructs the over approximation is by throwing away all the ReLU constraints. Okay, in your DNN, and I will show that in the example, and then I'll okay, so here, this is the model. You have seen this early on. Okay, this is for your benefit that I'm doing it. So the prepositional disjunctive structure comes because of this implication, because the implication is not of this or this, not of this or this. All the rest are conjunctions. Okay, as you can see, each of these is defined as a linear expression in terms of all the nodes that are feeding this. Okay, it's only the value of, when you try to express the value of this forward ReLU node, which you get this implication, and that is where you have a disjunction. Okay, so you can convert this into in this case, because there are two ReLU nodes with two conditions, there are 4 different cases possible. That is 2 to the 2. Okay, so you could, for each of these cases, you could split them. Okay, so like this. So for the case 0, 0, 0, 1, 1, 0, and 1, 1, and you can have 4 different things and then check each of them. And this original problem is satisfiable only if all the instances are satisfiable, but that's what you want to avoid. Okay, that is one way of doing it. Okay, now the question is, can you do this? That's why I call this as eager case splitting. Okay, converting the solving this one by eager case splitting and converting them into potentially a large number, a large number of separate LP instances. Okay, that is, you split. In this case, as it applies here, all you need to do is to take all the, there'll be one case, for every ReLU nodes. Okay, so if there are n ReLU nodes in your thing, so if you use this eager case splitting, you will get 2 to the n cases. Okay, that's where I'm saying it's exponential. Now, instead, what it does is, okay, now, and this is something that, this is, see here, this is a notation that is used to express an LP instance. Do you have any questions about this? Do you guys understand this particular thing? So here, what, yeah, there is a, if you know LP, how shall I describe this? Okay, so, what's an LP? See, there are, I mean, in LP, so this, it has, see, there is each of these internal nodes, the back nodes, is expressed as a linear combination of the inputs that are coming to it. Okay, that's what these equations are representing. Okay. Yeah, I mean, here you need to know, I mean, you guys have to ask more questions, okay? Otherwise, I'll be repeating the whole lecture. So how you decided, see, this is, an LP problem, okay, that has 3, I want to solve that x plus y is x plus y is greater than or equal to 0. Okay, that is this one. X plus y is greater than or equal to, where do I have the yeah, so I have x plus y, and that has to be greater than or equal to 2. Okay, that is one constraint. This is 2x minus y, and that has to be greater than or equal to 0. And S3 should be greater than or equal to 1, where the minus x plus 2y, that is the LP instance, okay? And you said, you have taken a simplex. I know that it may be resty, but the way it starts is for each of those linear expressions in the inequality, equates that into a new variable. They are either called slack variables or additional variables. And all the constraints, the lower and up constraints, the bound constraints are expressed on these things. And that's what this is. The original primary variables are only x and y here. And the constraint to be solved is x, as I just now described. Okay, and what LP does is it introduces new variables, equating them to each of the expressions that appears in your inequality, linear expression that appears in your inequality, and the bounds are, and their bounds are transferred into the corresponding bounds on the slack variables. Okay, so that's how this LP, this is the transformation that all simplex, does. Okay. No, not lower bound of x. X and y, the primary variables are unconstrained, okay? Because this is the LP instance that you're trying to solve, that x plus y is greater than or equal to 2. 2x minus y is greater than or equal to 0. So you're trying to, when I say solve it, you have to get the satisfying instances, getting some value of x and y, to checking if there is some value of x and y that satisfies all these 3 constraints. That is the simplex problem, okay? No. This might be because that's wrong. No. No. Okay. So if the problem is yes, let's assume that it's not true. So I think there was another point that I was trying to make. Okay. So okay, first let's assume that x is unconstrained. Okay. Yeah, it's minus infinity to plus infinity. So that's how that transformation is done. And that's what this table represents. Okay. So you have these equations, and for each of the variables, you have these lower and upper bounds. And to start with, the program variables have infinite, are unconstrained. Okay. And now what Simplex does is it goes through a sequence of pivot and update operations. Okay, it splits first those set of all variables into basic and non-basic. To begin with, all the slack variables are the basic variables, and this is this is basic and this is non-basic. Okay, now getting back, and then it does pivot operations, because some of the non-basic variables, it always keeps them the non-basic variables, they're always kept during this simplex in a state where they satisfy their input and output bounds. Now here, because x and y are unconstrained, they automatically they satisfy you start with some initial assignment. Okay, the initial assignment satisfies this. So maybe some of the bounds of the slack variables are violated. And then you pick the one that you whose bounds is violated among these basic variables, and then you adjust these non-basic value of the non-basic variables just enough to bring these one of the basic variables that is violating to either its lower bound or its upper bound. And that's what pivot and update. And then once you do that, you flip. You move the non-basic variable that is adjusted and make that basic. And then the one that, whose value got adjusted to fix, the non-basic variable which got adjusted to fix the basic variable, you split. Because as a result of that, potentially the bound of this non-basic variable, may end up violating its constraint. Because so during the simplex procedure, this, there's a lot of flipping that goes on, because even the slack variables can move, move in here. Okay, and then you keep doing this, okay, until you have all the variables, both basic and non-basic, satisfying their bounds, and then you have a SAT. Now, if you don't, if you cannot make progress, if there's no variables that you can actually find to fix them, then you declare it as unsat. Okay, so that's how the procedure is. Yeah, that is right. So there are two things in here. There's a small minor technical point that I was trying to illustrate through this thing. What if your program variables, in this case, there were no constraints on your program variables? No, your problem LP instance can say, oh, suppose in addition to these constraints, I also say that x must be greater than or equal to 2. Okay. Now you can always do this translation. So you would have, if I had stuck to this, I would have introduced another slack variable, just had S4 is equal to x. Okay, x I will keep it as unconstrained, and S4 I'll say must be greater than or equal to 2. Now, that is one way. That's one way to do. Okay, so that you can then, so you're unnecessarily introducing those, more slack variables. Although instead of that, when there is a constraint directly on the program variable, what it says is that you can have that bound, and as the first step, you can, as an initial assignment, if you're, instead of choosing 0, all zeros, you adjust the bounds of the program variables right at the start, okay, to make them satisfy, and therefore, and fix them first. After that, you keep doing the same simplex. Did you get it? That's yeah, okay. So because you had the question now, so that's why. So that's why I have shown that here. Yeah. No, no, no. I never said S. Yeah, yeah. So if you saw this, so I start with 0. And so as a first assignment, I will fix the, the program variables, okay? So after that, without actually doing any pivoting, okay, that's what I'm saying. There's a slight modification. Either I introduce S4 and then start my pivot and update, or a slight change I'm doing is, as a first step, you just get the program variables to get it to their bounds. And that's what I'm doing here, okay? Yes, S2 is, in this case, S2 is violating its bound. Yes, S2 is, yeah, S1 is violating its bound, okay? And S3 is too, correct? So, I mean, but I've chosen to fix S3. After that, you do pivot and update, yeah? Your observation is correct. So S2 has to be fixed as well. I mean, no, S2 is satisfying. S1 is the one that is, here it is violating. So S1 has to be fixed as well, yeah? So, but my point is, I don't want to go through this, okay? It's 2 points that I wanted to make, that's all. So instead of introducing extra slack variables, you can slightly modify the simplex procedure by fixing the program variables, bringing them into their bounds, and after that doing without actually pivoting that, okay? And then you pivot and update, okay? And you're right that you will have to fix whatever is all the basic variables that are out of bounds, okay? And that you do by actually pivot and pivot and update operation. So now I'm going to, and this I have illustrated. You can go through this, which I went through this, but after each pivot and update, these equations change. Okay, so here I did S3. I pivoted S3 with Y. Okay, and that itself fixed S1 also. Okay. It turned out, yes. In the beginning, yes, S1 also was violating, correct, okay. But when I did a pivot operation with S3 with Y, then so that it got, I guess it got fixed, yeah, and everything was fine. So this is another possible path to the solution that could have taken. That's what I'm giving it. So the whole purpose of this slide is to introduce this tabular notation. Any questions about the tabular notation? Yeah. We'll skip all these things. Now I'm going to, how am I getting an over approximation of this model as an LP instance, okay? An LP instance is represented as by the table and a tableau giving some equations, okay? And if you notice that here, every internal node, which is a backward node, is expressed as a linear combination of its, the nodes that are feeding into it. And the forward node, I mean, the node that follows this is expressed as a linear combination of the forward nodes of the ReLU node. Okay. And that is what is, so each of this is, the value of this is constrained to be equal to a linear combination of these things, okay? And the property that you want to verify is usually expressed as some constraint on your input, and some constraint on your output. Now, in this case, for illustration, okay, when you verify a property, usually it's a for all property, but you can also have I've chosen a satisfying property. I'm asking the question, if there is some, input, okay, such that the output can become, between 0.5 and 1. I mean, if I keep the input to be between 0 and 1, and is it possible to get an output which is between 0.5 and 1? Here it is possible, right? There are, and there is only exactly one, right? What is that? Okay. What should the input be? That makes this satisfiable. 0.5. Yeah, that is true. Anything in the interval 0.5 to 1, okay, will do. And 0.5 is certainly one of them. Correct? Yeah, that's right. So all the except for the constraint, I mean, that describes the relationship between the forward and the backward node that form a ReLU pair, the input and output. All the rest are linear, can be expressed as linear equality, okay? Because this is equality, but it only here that you have some nonlinearity. Therefore, this model that I have in here, I'm introducing, one equation, a slack variable that represents the relationship, this linear relationship. So all these A1, A2, and A3, they express the value of denote the linear expression that defines the value of the backward nodes, and as well as V31 in terms of V21 and F. Okay, so that is. So your constraint is this has to be equal to that, or you're pretty much saying that, so you convert that into an equation and then say that the constraint, the lower and upper bound has to be 0, okay? Right, because they'll have to be exactly equal. Yeah? Yeah? Why? Because no, this is what you want. I mean, in this case, as an LP instance, you want to first express, you want V11 to be between 0 and 1, okay? And you want to check, you check the satisfying instance, V31 to be between 0.5 and 1. Now you'll have to come up with what the bounds for the inputs, I mean, for the internal nodes are. Now the internal nodes can be anything, okay? Except that they'll have to satisfy this should be equal to 0, this should be equal to 0, this expression should be equal to 0. That is part of the constraint. As an LP constraint, there's equality constraints is what it is imposing. Okay. Now, normally you would describe it as less than or equal to 0 and greater than or equal to 0. Okay. You could do that. Still, you would be introducing 2 slack variables or 1 slack variable with saying it is greater than or equal to 0 and less than or equal to 0. That's all that I'm saying here. So how would you express equality in terms of inequality? I mean, in order to do this, you would say that this can be anything except that this should be V11 should be equal to V21B, which means you're saying V21B minus V11 has to be equal to 0. That is the constraint of the model. Okay, and that's what is being expressed. Why would you want to throw it away? you want to get, in order to see if this is satisfiable, you have to get some values for all these internal nodes such that they satisfy whatever constraints on them, and also along with these constraints. That is what you have to do. So in order to express it as an LP, you have to come up with constraints on all the internal nodes. And these are the constraints on the internal nodes. Okay, that this should be equal to 0, this should be equal to 0, and this expression should be equal to 0, right? And that, and whenever you say that is equal to 0 in LP, you will introduce a slack variable for that. And then you fix the lower and upper bound. If it's an equality, it is always going to be 0. The lower and upper bound is to be 0. I don't understand. No. First of all, why is this? This is an LP instance now. Okay. Yeah, in this case, your inequality is that this expression has to be equal to 0. It has to be equal to 0. Okay, that means it has to be less than or equal to 0, and that has to be greater than or equal to 0. And that's an expression. So you would have, if you were converting normally into LP, I'm not doing anything non-standard here. So equality is expressed in LP as it is between the bounds are less, 0 and 0. That's all. How can you make it more efficient if you want to use that standard form for transformation? No, but see, you're missing the point. Okay, LP is always some linear expression less than or equal to or greater than or equal to 2. That's how the LP instance is defined as. It does not have something. You can have something equal to something, but standard, we are assuming that the standard form is some expression is between two constant bounds. Okay, and that's how I'm expressing this. Okay. So that's, that's all. Now, if you can come up with a more efficient representation of LP that you can actually come up with a new algorithm for simplex, that we can discuss separately. Now, I'm assuming that your starting point is some set of linear expressions is between two constant bounds. Okay, and that's exactly what I'm, doing here, because eventually there is some constraint here on V11 and V31. And there are constraints that define, equality constraints that define these internal nodes in terms of their input feeding into it. And the reason this is an over approximation, okay, is because I'm not imposing the actual ReLU constraint between these ReLU pair of input and output of each ReLU. What I'm saying, I'm only saying the input V21B into a ReLU can be, okay, is unconstrained. The output has, since I'm using, if then it's a max of those things, I'm just saying that it has to be non-negative. Okay, that much of information I'm using. All the rest is I'm throwing away. Okay, because actually, there is a lot of it that's lost. ReLU nodes satisfies your input. V of F must be equal to max of 0 of B of B. Okay, that is the biggest thing. That is, a max can also be expressed if then else. Okay, not completely. Okay. Part of it is there. That's the point that I'm making. The positive part, the non-negative part is there. Okay. So in that sense, it's not the full thing. So this is, why do you want to? I mean, if you're able to express some constraints and still keep it as an LP, I want to include it. No? So this is as best as I can do, okay? And then still, I mean, as best as I can do to, throw away. I mean, I could have put this as minus infinity to plus infinity. That'll be even less precise of an over approximation. This is slightly more precise of an approximation, okay? But how would you do that? Then you're getting into this kind of a formula. It will no longer be an LP. Idea is to use LP to solve, because if you want to check the satisfiability of the model, this model is not an LP by itself. If you expand, you're getting R. So I'm basically throwing away that R, okay, here. You cannot, it's not hard. It's not possible to express it as LP, because LP is just a conjunction of linear inequalities, okay? So this is one way. I mean, basically what I'm saying is I cannot express max because that requires disjunction, but I know that max always is returns something max of this 0 in VB, where VB can be anything, the entire minus infinity to plus infinity. Then I know that it is always going to be non-negative, so I only keep that, because non-negative, the fact that non-negative can be expressed as a linear inequality. Therefore, the idea is try and solve this, okay, is what. So now this can be solved as an LP. Now, and for which you will use the standard LP rules. And that's what, and this is precisely the idea, okay? I only have 10 minutes because I have to leave at 6 o'clock. Or if some of you are willing to stick around, they can do. So let's see. So you start with an over approximation. So the first thing is any doubts as to how you construct the over approximation, okay? No, I'm using the standard LP thing, okay? So if indeed you can come up with some special way of handling equalities, which is the point that you were doing. I don't know if there are simplex variables that actually do. Maybe they do, maybe they do. But in terms of, their expression is less than or equal to 0 and greater than or equal to 0. And that's the encoding that I'm using. And you solve this, invoke LP. If no solution exists, then you know that it is unsat. But if it does, if some solution exists, then you're not sure if that solution is an actual real solution for this. That you understand, no? Why? Because the ReLU constraint is abstracted. So you have to check, even if there is a thing, then you can, that indeed the ReLU constraints are checked. And that's what you do. Check if alpha satisfies the ReLU constraint. Now that you could do. Checking is very efficient, okay? Because LP gives, if there is some, like you said, in this case, it is possible. There'll be, you can bring V2 F to be 0.5, okay? And you can fix that we will see. So you can change, because V2F is between, you can make V2F, V21 of F to be 0.5, okay? And then, it is one of these that will be violated, because A3, because to start with, all of them are 0. So this will be, A3 will be 0, okay? But you want, but this one says V31 has to be between 0.5 and 1. That's a program variable. That's a variable. So you will have to first change this V31 to be, like I've said, 0.5. That will make A3 become 0.5. Okay. Therefore, it's violating that. And one way to fix it is by pivoting with V21 of F. Okay. And so this becomes V21 of F becomes 0.5. Then everything is satisfied. That over approximation satisfies that. That's a simple LP call. But unfortunately, that will violate. Then you go to this step, check if that satisfies all the ReLU pairs by checking that. where did I write? I wrote something. That max thing. Now, for a given LP solution, checking it is very simple. Okay. So in this case, you will see that there are so V21 of F is 0.05, but this is 0. So this ReLU pair is broken. And that is where, so either you have to bring this back to 0, okay, but then you are back to square one, okay, which will not, and the update rules are defined very cleverly so that won't happen, okay, that is not done. Or you can bring it up, you can increase this to 0.5, okay. Now, that will of course fix the thing, but maybe it'll break. Let's see if it breaks something else. Okay, so if you bring it up to 0.5, then well, you will it, and that's the idea. Okay, so you fix them separately to by updating either the input or the output thing, and then yeah, then you will fix it, and then you have to go back to step 2, because in general, fixing these things may violate, may make some of the other variables violate, because you're doing it willy-nilly, okay, just by to making that satisfied, because they're all interdependent. This might end up violating something something else, and therefore you have to rerun your LP again. Okay. Now you might be lucky, okay, that you keep doing this. Okay, so there'll be up to, and then maybe without actually case splitting, you may end up. Okay, there might be a way that you can actually fix all these ReLU pairs through a sequence of LP calls alone, and you do the case splitting. Now, how long can you do that? Okay, now that is where this thing is. There's no guarantee that just by fixing locally all these ReLU pairs by repeated LP calls, you will get a solution. Okay, so it does the next to best thing, or you can keep on running, and maybe one ReLU pair fixing will bring you back to some original state, because see, in the simplex case, there was a very careful, just the variable ordering allowed you to, it guaranteed that you will not, no state will recur. Okay, here there's no such guarantee. Okay, so therefore they do a very simple thing. You do it, you try to keep repeating this loop and put a bound on that. Okay, and now that bound, how do you determine? That's a heuristically determined, or you do up to 100 depending upon your resources, or you can do a simple, something like that. And then still, if you don't have a solution, then you case split. And that's why I call this this approach is called lazy case splitting. Okay, so but there are a lot of cases in which you could end up getting a solution. And in this simple case, it is true. And I'm going to, I'm just showing in this case, you don't need a case split at all. Okay, but if you were to case split, in this notation, case splitting just means that you are propagating these constraints. Okay, and that is, you can do it simply, okay, by changing the lower bound or the upper bound. Okay, and these two, if you had to case split, okay, in step 3, this is what you would do, and you will solve. You have to check this is satisfiable as well as this is satisfied. Okay, yeah, but it turns out in this case you don't need a case split. But if you were to case split, just this shows how you could express it as 2 individual LP instances by just fixing the lower and the upper bound corresponding to these these cases, because the ReLU constraint is so linear. I mean, that relationship is linear. Now, in general, if you were to using Z3, or in program, what if this case, the Boolean condition itself is so complicated as or, and so on, then you won't be able to simply express it, do the case predicate expresses as an LP. But in the case of DNN, you can exploit. It's its own structure as a programming structure is quite limited, okay? And that's why you're able to case split and then keep each of the cases as LP. And this is what the sequence of thing that goes, okay? So this I pointed out. So 0.5, and there is a ReLU violation. You fix that. And the way, I mean, the constraint in the update is, it says that you shall, update only, I mean, among the ReLU pair, when you're trying to fix it, you can update one of, that, okay? One of them has to be the one that you update. You have a choice of updating either the forward or the backward variable to make it satisfied. But the condition is that it has to be a non-basic variable, okay? Because it's the non-basic variable that you normally adjust anyway, okay? Even during in simplex. And that's why they want to keep that, okay? So that non-basic variable. And also there is another thing. See these, you are adjusting these ReLU pairs and there is no constraint. The backward variable, for example, have minus infinity to plus infinity, okay? And and this also has fairly liberal constraint between 0 and infinity, okay? Therefore, so that is one condition. So here, as a result of fixing that, yeah, you update the backward variable because you cannot update V2 of F. Okay, firstly, you have to decrease it, which will bring back to the thing, and see, it's already been flipped. And it is now a basic variable, and therefore that's by putting that restriction that you shall only update, if you update a particular thing, that it has to be a non-basic variable, will prevent you from going back into where you started. Okay. Now this will, I think, A1. As a result of this, A1 will become. See, you made this to be 0.5, but obviously, so V11 could be anything between 0 and 1. So you will have to, it has, because that will violate. A1 will violate because you have to, the satisfying instance has to put the constraint that V11 has to be between 0.5 and 1, okay? If it is 0.5, actually it has to be 0.5, now V11. And that's why A1 gets violated. That can be fixed by pivoting A1 with V11, and which makes, and the adjustment, this is simplex adjustment, standard simplex adjustment. So it's the second LP call that you're, that you're making. Now this will be, here you will have all the ReLU pairs satisfied, and that's why yeah, I think you will have to make this thing satisfy as well. Okay, can you just go? I'll take a couple of minutes. That's all. And why? Okay, there is A2. It says A2 is also violated because if it is 0.5, A2 is defining so V22B will have to be set to, why is A2 goes out of bound? A2 is defining V2, that's what is adjusting V21B, no? V21B gets 0.5. And this is V22B in this case is already, because if this is 0.5, because we started with V22B as being 0, no? So in order to make it consistent, this is has to be minus 0.5, okay? And that's what is being assigned here, okay? So V22B will have to be minus 0.5, right? Once you do that, the simple LP. So there are 3 LP calls, okay? Because you will have to fix this as well, because this cannot be 0. If this is 0.5, okay, this has to be minus 0.5, and that's what this fixing is doing. V22B, okay, and that requires the third LP call, and after that, all the pairs, I mean, all the ReLU pairs of things, and that's the idea, okay. So I will just show you this one. The crucial thing is, see, xj is always greater than or equal to 0. Why in this case he puts this as a constraint, I don't know, okay, because see, these updates are always called after a successful LP on an over approximated model, okay. Therefore, since you're already starting with constraint to be 0, between 0 and infinity, so this condition will be satisfied. That's my claim. So, but the important thing to notice is you update only if you update the in the backward and the forward. It has to be non-basic. Now, if neither of them is non-basic, then what you do? Then here it says you pick something else, okay? It is either either the backward variable or the forward variable. You pick something and you pivot it. So you can always do pivot operation without update, okay, in an LP, because all you're doing is you are changing the linear, you're expressing a different set of things as linear combinations, okay? So this is fine to do, and this allows you to when you get stuck and without any update, it allows you to maybe try more updates that are possible. And that's what you do. And then ReLU success will have to be modified, because in addition to ensuring that your LP, all the LP bounds are, the normal bounds are satisfied, you also have to check all the thing. Now, in the worst case, you have to split, and this rule is there for the splitting, okay. Now, if you have any questions, I mean, I'm going to be giving assignments. So because when this, I should have already given it, because these things, normally you will have to work on some examples and exercises. Otherwise, there's a lot of details here to actually for you to digest, okay? And, so hopefully, for this course, you will have to spend some time during this midterm. Okay, for this course, for that, I'm going to give you some assignment, so it will help you, exercise your mind to what has been covered until now in terms of the theory. Okay. No, I think what I will do is there are these basic lectures that Diganta will have a couple of lectures, Madhukar one, that covers the basic part, So the exam syllabus for the quiz or something that I will give you will be that. After that, it is all, those papers, okay, that will be, as I said, I mean, they'll have to cover that now. So there are 3 or 4. So I would imagine it'll be some mid of the second part of the thing, so that you won't forget. Okay. I told you middle of next part. Okay. So yeah, that's my idea. But that